All right, so had this been a normal calculus semester with me, one without all the distractions and the unfortunate events that have set us back quite a lot, we would move from indefinite integration, where we were thinking about integration as the antiderivative operation. Okay? Then we would have proceeded, it would have looked somewhat like we had divorced calculus for a little bit, and we would have proceeded into discussing areas under curves using Riemann sums. Then we would have what would have looked like the two techniques of antiderivative of areas under curves and antiderivatives. What would have at first seemed like divorced topics would have been brought together as one in the end. So, but given the time constraints, we are going to skip over Riemann sums, and I'm going to, as well as skip over a lot of the proofs, which some of you, by now you know me, and you know that that's not always easy for me to do, but I want to get you to the next topic, which is definite integration and areas below regions, right? So we'll talk about areas under curves, and then that'll be the topic of this video. And then the next video, I'll show you how they are related. Again, without all the algebraic preliminaries and limits and things of this nature, we just don't have the time. Now, let me see if I can guide you here. So, what do I mean about areas under curves and how that has something to do with areas have something to do with calculus, right? So let me see if I can guide you through this example, a few examples first. So let's start with the basic rise over run slope formula that all of you would have encountered probably fairly early in your math career, where you just have y sub 2 minus y sub 1 over x sub 2 minus x sub 1, which is equal to the average rate of change or the slope of a line, correct? Now, it's fairly easy to move from slope to point slope. As you can imagine, I'm just bringing that denominator to the other side of the equation, and such that now I have solved for y sub 2 minus y sub 1. Now, I don't intend to venture down this path of how do you find slopes and how do you go from point slopes to equations of lines, right? That is, you have mastered those skills. Here's what I want to tell you really quickly. All right, are you with me? Are you with me so far? What if I told you that you can think about y sub 2 minus y sub 1, okay, as the area under a curve? What if I told you that they are indeed the same? Well, what do I mean by that statement? So let's just assume, so what I've drawn here, some graph of some linear equation y, right? So here's some line going about, and you know how we would interpret the slope. So this would be this very first point here. When you at x sub 1, we have a y sub 1, and at an x sub 2, we have a y sub 2. So that slope formula is basically making a statement with, for every change in x, what is the change in y, right? Well, let's start with the change in y. It's very simple. I mean, if you are at the second y value and then you were to drop down, right, hold on. If you were at the second y value, you were up here, and you were to drop down to the first y value, I know my language is somewhat sloppy, but you understand what I'm saying. How would you figure out how much of a fall you took? Well, it's just simple. You start with your first height, y sub 2, and you subtract where you ended up, which is y sub 1. That'll tell you the drop, right? That'll tell you the You can think of it as the rise or the fall. We'll call it a rise. That's how much you rose. And so you can think of it as you jumped. You started here. Y sub 1 jumped to Y sub 2. Okay, and then what about the change in x? Well, again, it's just a matter of thinking about you started at x sub 1, then you stopped at x sub 2. So how far did you travel? Well, just take where you stopped minus where you started, and that'll tell you how far you drove, right? And this is the exact this triangle that you're seeing represented here just makes perfect sense with how we've always thought about slope. Now, let me ask you a question. Let me write that equation: y is equal to mx plus b. That doesn't look like a b, it looks like a 6. Let me change that. So y equals mx plus b. Now, I know, and you know, that is a line. That's the equation of a line. So if you were to take the derivative of that, does it make sense to you that the derivative of y would just be what? Well, let's start with, what would the derivative of a constant be? Well, that would be 0. And then you would take the derivative of mx, m being some coefficient. That would just be m. Just like the derivative of 2x is 2, the derivative of mx is m. I don't think you'll argue with me very much. And now let me ask, well, what would the graph of y prime look like here? Well, don't you agree with me that m, the slope, is some constant, right? There's no variable attached to it. It's the slope is the same throughout the entirety of the line. If the slope was 3, it would be the slope would be 3 throughout the entirety of the line. So if you were to, for example, if m is equal to 3, if you were to graph that, that would just be a horizontal line. The same, if you were to graph m, that would also be a horizontal line. So let's see if you agree with the following. So if I graph m, let's just say that it looks like this. It would be m, right? And that's the graph of, in this case, y prime is equal to m. Horizontal line, no problem. Well, hold on for a second. I just got done making a statement that you can think about the change in y, right, as an area. And here we go. Let's just finish it up. So if you were to plug x, well, don't you agree that no matter what you plug in, no matter what x is in this equation, that y prime is always going to be the same number, correct? There's no variable to even plug for x. So at x sub 1, y prime is m. At x sub 2, y prime is m. Now hold on, that's interesting. In this particular case, you have created a rectangle. And interesting enough, the area of a rectangle is just the length multiplied by its width. If you don't mind, let me just say that is a height multiplied by width, just so we can use the same language. So in this case, let's talk about if we were trying to figure out what the area of that triangle be. Let's start with the height. So what is the height from here to here? Right? Length, width, I don't care. I don't like length, height, I don't care what you call it. But what is that distance? What is that? So, well, that height would be equal to m. And what would the width of this rectangle be? Well, the width would just exactly just be the x sub 2 minus x sub 1. Well, that's interesting. I think we've seen that before. M multiplied by x sub 2 minus x sub 1 can be thought of as the area under this derivative, which is equal to, right? This is equal to the change in y. So that's interesting, because when I first went through calculus, I thought, well, man, are mathematicians just obsessed with finding areas? Is areas under various curves? But I never, at least at the beginning, I didn't quite realize that, wow, areas under the curves, although that may be useful in and of itself, but areas under curves can be used to find a change in y. Now, let me show you a more concrete example. Okay, one that you can follow a little bit more easily. Ready? So in this case, we have a cost function. Now, for here, x is how many units that you produce. I don't know what you're producing, but x represents how many of those units you do produce. So if you produce 1 unit, you would plug 1 in for x, and then what would come back out, c of x, that would be the cost of producing 1 unit. With me? Now, we're told that x can vary from 0 to 20. In other words, you can produce absolutely no units, or if you really ramp it up, you can produce at a maximum of 20 units. That's the most that you can produce. Now, I'm gonna ask a very non-calculus question. I'm gonna ask, what is the change in cost as you increase from x equals 5 to x equals 10? Okay? So what I'm going to do right here is I'm going to show you a non-calculus way of thinking about this question. And then I'm going to show you how that ties into areas. Are you with me? Okay, so right now, let's assume that you're producing stuff, selling it on eBay. And right now you are producing 5 units. So let's find the cost for producing 5 units. Well, C of 5, well, that would be 180 multiplied by 5 plus 200. Okay, so in this case, if we grab our calculator, and let's figure out what that is. So 180 times 5 plus 200, I think that's going to be 1,100. 1,100. Okay. So right now, again, you're producing stuff, you're selling it, say, online, and it's you're only producing 5 units, and you got a cost of $1,100. But you've decided, you know what, I'm going to ramp this business up. I'm going to take it to the next level. I'm going to start producing 10 units. So now let's figure out what the cost would be if you started producing 10 units. Well, okay, well, that would be 180. Let's do 180 times 10 plus 200. In other words, 180 times 10 plus 200 would be 2,000. So now you got $2,000 in costs. Okay, so the question was, the question read, what is the change in cost? Right? I mean, clearly you have more cost now that you're producing 10 than you did before when you were producing 5. So the change in cost would be C of 10 minus C of 5. Right? In other words, 2,000 minus 1,100. So that gives me $900. That's the change in cost. Okay, so boring, because that doesn't appear to be at the level of mathematics that you are at. So now, let me do this. So I want to ask the same question, but I want to interpret it a little bit differently. I want to interpret it as an area. So the first thing I want to do is, let's take C prime. Right, let's take the derivative. All right, well, the derivative of 200 is going to zero out, and the derivative of 180x is just 180. So notice how C prime is equal to 180, and I'm going to go ahead and try to graph that. So let's just say that this right here is the horizontal line, 180. Maybe it'd be helpful if I drew a better horizontal line. How's that? So this is at 180. Okay. And now, again, notice how we can think of this as a rectangle. And notice we can think about the area of this rectangle. And it's very important. Notice that this is the area under what? Under the derivative. Right? So this is the area under the derivative bounded from 5 to 10. All right, well, you know what to do. So if you want to think about this as an area, length times width, or height times width, or you'd like to think about it, let's go ahead and plug in. This should be pretty easy. So this would be area. Let's start with the height. So I think you'll agree with me that the height of this rectangle is 180. And the width of this rectangle, right? Well, the width is 10 minus 5, which is just 5. And if you happen to have your calculator readily available, what is 180 multiplied by 5? 900. Interesting, right? Does that interest you? Interesting that the area under the derivative was equal to the change in y. Okay, so let's put a pin in that for just a second, right? Maybe we'll come back and we'll see if we can formalize some of those things. So let's actually look at how we might find the areas under curves. Now, notice the difference between the integral that's written here compared to the integrals that we were doing in the previous videos, right? What is actually different here? Look at the difference in the integrals. Well, now we have numbers in what we call the lower and the upper bounds of our integral. Okay, so let's go ahead and continue here. So do you recall, let's see if you recall. Do you recall what the title that we gave the piece that was inside the integral, right? What was this, the title of this? Well, we called it the integrand. But don't you recall that this was also the derivative, right? What we integrate is the derivative. Right? So if you have the derivative and you want to get, if you start at your dy dx, you got your derivative, and you're trying to get back to just regular y, well, that's what you integrate your derivative. So the integrand was our derivative. So let's start with what would the graph of 4 look like? Now, you've already seen me do this multiple times, so this is getting a little bit old at this point. But I'm gonna go ahead and work through these a little bit faster. Ready? So let's go ahead and graph. Let's start with graphing the derivative. Now, don't worry about these tick marks. This is the graph of 4. Don't worry if these line up, the tick marks line up. Okay, so that's the graph of 4. And then now to ask what's the area under all of this, well, that's infinite, right? So that we're not going to have a finite area under the entirety of that curve. But if you bound that curve, right? If you have a starting point and a stopping point, then you'll have something you can find a finite area of. So in this case, notice that this 1 in the integral represents the starting point on the x-axis, right? So that's the first bound. And this other number that in the integral is, so again, I'll write this as the lower and the upper bound. Okay, that 3 would represent the starting or the stopping point, I'm sorry, of x. So it's x starts at 1 and it stops at 3. So now we've bounded, and the question is, notice that we can, the question of the integrating 4 from 1 to 3 with respect to x, we are going to now think about that as the area under this curve from 1 to 3. All right, now I'm going to kind of go through this part a little bit faster because you've seen me do this twice. So the width here is what is 2, and the length or the height would just be 4. So when we find the area is going to be equal to 2 times 4 or 8. All right, so what is that 8? That 8 is the area under that curve from 1 to 3. All right, so let's keep going. So now let's look at part B. So the very first thing we're going to have to do is graph x plus 2. All right, well, the good news is x plus 2 is just a line, right? So that's fairly easy to graph. So let me see if I can go ahead and graph that really quickly. All right, and what we would know about that would be, you would think about, just in case that's confusing to you, you would think about this as, let me get a darker color here. The way you would think about this as y prime is equal to x plus 2. Okay, so that's the graph that we are graphing right now. So, all right, so that would mean that when x is 0, this would be 2 right here. And okay, so to ask about the area under this curve is going to be infinite unless we can somehow bound it. Well, that's the good news. The good news is with definite integration, they tell us how to bound it. So we're going to start at x is 0, and when x gets to 3, we're going to stop. So when x gets to 3, so here's where x is equal to 0. When x gets to 3, that's where we're going to stop. All right, now take a look at, I'm gonna do my best to shade this in. So take a look at this shape here, right? Because you want to find the area under the curve from 0 to 3. Now, I know that you might not have a lot of these formulas readily available, but first let me just, that obviously we have a 4-sided, right? We have 4 sides to this figure, right? This is a quadrilateral for sure, and it actually is a trapezoid. Now, do not get caught up in, wait a minute, how would I would not remember, I would not remember the formula for the area of a trapezoid, right? So I don't want you to get caught up there. So, but a trapezoid, and I'll go ahead and write the formula for the area of a trapezoid. We would have area is equal to 1/2 multiplied by, we have height, and then we have, normally what they use is little b sub 1 plus b sub 2. All right. So what we need to do now is figure out the way we would look at the height, and b sub 1, b sub 2. Okay. So the sides that are running parallel to each other, right? So notice that this side of this quadrilateral and this side of this quadrilateral, these are the sides running parallel. Notice that one is larger than the other. Well, the first one is b sub 1. And the second one is b sub 2. Okay? Now, the height, or the altitude, would be the length from here to here. All right, well, let's start with the easy one. So in this case, we would have area is equal to 1/2. Let's start with the height, which is just 3. And then we need little b sub 1 and b sub 2. So the first one's easy, right? The b sub 1 is going to be, has a length of 2. And then how would you figure out b sub 2? How would you figure out this length? Well, very simple. You would just have to plug x is equal to 3. You would have to plug 3, right, in there. You look it up here. You would have to plug 3 in for x. And then you would figure out what the height is. So if you plug 3 in, you would get a height of 5. So I know that b sub 2 is 5. So what is that? That's 1/2 times 3 multiplied by 2 plus 5. So in that case, the area is equal to 21/2. All right, so that's the area of that trapezoid. Last one. So now, how do we think about the area under this curve? And more importantly, how do we even draw that curve? So let me see if you, does it make sense to you that, well, let me write it this way for just a second. I'm going to erase this in just a second. Let's think about if you had y squared plus, let's just say x squared plus y squared is equal to 1. Now, if you were going to solve for y, by the way, so what would that be? That would be a circle, right? That would actually be the unit circle. So if you solve for y, you would have y is equal to plus or minus. Now that plus and that minus is important because it would be the square root of what? Well, you would have, in this case, it would be 1 minus x squared. So if you were to grab your calculator and graph the positive, the positive square root of 1 minus x squared, you would get the top half of that circle. And if you were to graph a negative square root of 1 minus x squared, you would get the bottom half of that circle. Now, notice what we have. We just have the positive version of the square root of 4 minus x squared. So in other words, this is not a full circle. This is a semicircle. So now let me go ahead and erase this. All right, and now this graph doesn't quite go out far enough because what we really have, I'll show you in just a second. What you really would have had in this case would have been x squared plus y squared was equal to 4. When you solved for y, notice that we only took the principal square root, or the positive version of the square roots. That's all we have is the positive version. That would be the top half of that circle. And the radius here, this is the radius squared. So the radius is squared is 4, so that would mean the radius is what? The radius would be 2. Okay, so that's how you can notice it. We're going to go from -2 to +2. So let's start by representing that. So let's just say here's where x is -2. And let's just say here is where x is +2. And that is a semicircle. So it's just the top half of that circle. And it will go, I'll do my best to draw it. There we go. Good enough. Okay. Well, how do we answer this question? Because obviously this doesn't look like calculus to me. And I agree with you. It does not look like calculus if you're thinking the same thing. And so area of a circle is pi r squared. But we don't have a circle, right? We have half of a circle. So the area for a semicircle, a half circle, would be what? It would be pi r squared over 2, because we only have half of a circle. So now what we want is we want the area of under that region from -2 to +2. Okay. So to do this is fair. All we need to know is the radius. Now, in this case, the radius of this circle would be 2. So if you plug 2 in for the radius, right, so the radius is equal to 2. So what is the area? Area is going to be equal to pi multiplied by 2 squared divided by 2. Well, that's interesting. So that's 4 pi over 2. 2 squared is 4 pi over 2, or 2 pi. All right, I agree with you. This is not calculus. And we are almost done with this section. The only thing that I'll do is I'll just kind of tell you a little story really quickly. Ready? We all love stories. And mathematics has lots of stories. I wish our professors would tell more of them. Now, what's interesting is, although we have, for a typical semester of calculus, you start off with the study of the derivative, right? The differential calculus. And then you move to the study of the integral, the study of integration. But integration has actually been around for quite some time, right? For much longer, for millennia. And if you had to look into why would mathematicians, be interested in areas, thousands of years ago, well, probably because they were contracted by the states or the powers that be to approximate the areas of land so that they could figure out how much to charge in taxes based on the land, right? So if you had everything's nice and neat, if everyone's land was, met some geometric shape that we had a formula for the area of, but if you had a property line that looked like this, well, there is no readily available, well, there is no geometric formula at all that you can call on to find the area for something like that. And let me tell you a quick story with how we'll use just the circle, okay? So this little problem plagued mathematics for a long time. And I'll talk to you about the way that the Greeks tried to tackle finding the area of a circle. So first off, let's notice that the radius of this circle is 1. Now, so we have no idea what the area under this circle is, but let me show you the way mathematicians such as Archimedes would have tackled this. So what Archimedes would have done would have been to start by using a geometric shape that he did know the area of, right? So rectangles are very easy to find the areas. And notice that we have an inscribed rectangle, right? We have a rectangle that is fully inscribed inside of this circle. Now, do you agree with me that it would be easy to find the area of that rectangle? Then let's you and I also agree that area of that rectangle does not match the area of the circle, right? Do you see all of this? All of this is error. You would have missed all of this area. But we do know that the area of this circle, if that is going to be larger than this rectangle, right? In other words, you have found a lower bound. You know it's going to be greater than the area of that rectangle inscribed. And then what mathematicians would have, like Archimedes would have done, would have been to place a rectangle outside the circle, so to circumscribe by the circle, so such that the entirety of, notice that the entirety of our circle is nestled between these two rectangles. We know that if you found the area of the outer rectangle, that would be too much, right? You see all this? This would be area that would be too much. But you have an upper bound. And now let me pose a question to you. How do you think mathematicians like Archimedes would have done a better job? How would they have approximated the area of the circle better? What could they have done? Right? This is while you're thinking about this, I'll just draw. This is the area of the circle. This is what we want. And we know it's going to be greater than, I'll just write inner instead of writing inscribed, greater than the inner rectangle, but less than the outer rectangle. And time's up. So there's a lot of error here. And my question was, how could they have done a better job? Are you with me? Well, see if you agree with this. See if you were thinking this. What if you just increase the number of sides? Right? What if you would have done, and it's hard for me to draw this with a stylus, but what if you would have done instead of using a four-sided shape, what if you would have used a five-sided, a pentagon or a hexagon or an octagon, or in other words, what if you just kept increasing? Let n be the number of sides. Right now, n was equal to 4, and we have a lot of error. What if you kept increasing the number of sides? Right. So, and this is actually true. If I recall, I believe Archimedes used to draw these inscribed and circle rectangles and circumscribed rectangles, these polygons in the sand with using some type of stick, would have drawn out some 20-sided, 10-sided figure in the sand while he was thinking. But each time you increase the number of sides, you would do better. You would have a better approximation of the true area of the true circle, right? And now comes the question of, well, what if you were to increase the number of sides by letting the number of sides approach infinity? You're starting to connect it, right? And then what would that do, and how could that help us determine the area? So for another time, for another video, we'll start to discuss that. I will tell you a quick funny story. If I recall, when Archimedes was he was fairly up there in age, maybe of the age of in his 70s. So he's out wandering in the sands, drawing his circles, and deeply invested in his work, and as the story goes, that has no idea that his city of Syracuse is being sacked, is under attack by the Romans. And the story goes that a Roman soldier walks up to Archimedes while he's out there drawing in the sand, this mathematical genius just drawing circles in the sand. And the Roman soldier turns to Archimedes and says, you have to come with me. And Archimedes says, "Don't disturb my circles." To which the Roman soldier kills Archimedes. And that's the way the story goes. I just can imagine Archimedes is worried about his circles. Don't disturb my circles that he's drawn in the sand. I hope you found that interesting. I found that very interesting. See you soon.